Thank you very much for being here. We're going to be talking about our all-in-one RISC-V AI IP. I'm Roger Espasa, CEO of Semidynamics, and I hope you find this interesting. Okay, about us, we're a European company founded in 2016, 100% R&D engineering. We got some sales around the world, and we focus on customized RISC-V AI cores, right? And I'll be talking to you today about how we do this all-in-one AI IP, right? And before I start talking about what we do, let me talk about what everyone else does, right? All the new SoCs in the market have this requirement of very, very high AI needs, right? Everybody wants to put AI on their chip in one form or another, right? And what people end up building is something like this, which is not what we recommend. So people put a bunch of CPUs, and we're in the RISC-V booth, and obviously what we want is that they put RISC-V CPUs, but other people put other CPUs. Then they put an NPU, which has lots and lots of integer maths, and then usually they also put a GPU, right? And why do they put a GPU? Because the NPU is great, but does only one good thing: convolutions and matrix multiply. Everything else you need to do something else, right? And what's the problem with this architecture? It's very hard to program. 1, 2, 3 software stacks. Probably a RISC-V one, a proprietary one, and another proprietary one, right? Very high latency. When the cores want to talk to the NPU, they have to either program DMAs or write secret registers. It's very long latency to talk from one to the other. It results in non-optimal PPA. You're building a silicon, you want the best area, best power, best performance, and what happens? Well, you end up repeating caches, you end up putting DMAs, you end up doing lots of stuff, right? I said 3 software stacks, I'll repeat it now, that you end up with 3 totally different software stacks. And the thing that's most worrying if you're building a silicon device, right? You're building a silicon, it's going to take you 2 to 3 years to build the silicon. How do you know your AI is going to work when the AI people invent something new? How do you know they're not going to invent the next generation of ChatGPT in October, right? How do you make sure your AI works, right? And this architecture is not resilient. Instead, what we suggest, what we propose, and what we tell the world that they should do is actually build this simpler element, a RISC-V core, connected to a vector unit, and connected to a tensor unit using the RISC-V ISA. So no DMAs, no strange software environments, all RISC-V, right? Once you have this element, and let's make a number, this tensor unit does 4 teraops, right? Now a customer comes and says, well, but I need a 40 teraop solution because I'm doing a camera for a parking lot, whatever. Well, just put 10 of those. These are cores, these are Linux cores. You have Linux, you know how to connect 10 cores. This is easy. Don't go with this other complicated architecture. Use a simple one, all based on RISC-V, right? It's easy to program, I'm repeating myself, but only RISC-V, so one software stack. It's high performance. There's no copying data here. You get some data here, you process a matrix multiplier or convolution on a tensor unit, and immediately you use the results in the vector unit. No data copying from one side to another, nothing like that, right? Better PPA. You notice the black boxes in the previous slide? If you didn't, I'll give you an exam later. But if you're saving SRAMs, you're saving caches, you're saving data movement, you're saving energy effectively, right? So you're saving power. Resilient to new AI. Why do we say that? Well, you have a fully programmable vector unit. You have a tensor unit that does convolutions and matrix multiply. Whatever the AI guys invent, this thing can run. Because they do now a recurrent network. I know this is already invented, but now they need recurrence, and they need branches, and they need, I don't know, some layer that's new. No problem. They'll do the convolutions here, and then they'll do the layer in the vector unit. And if they need complicated control, surprise, they have a full RISC-V core to deal with that. So that's why we say that this should be the right architecture for the future, right? Unified programming, only RISC-V, only Linux. Of course, if you want to do bare metal, go ahead, you can do bare metal, but only Linux. And repeating and closing, one software stack, right? It's all RISC-V. There's nothing more. It's a bunch of instructions, and if you guys understand load, multiply, you also understand vector load, matrix multiply. Same thing, right? Debuggers exist, two IDEs exist, libraries exist. You get the comfortable programming environment you're used to. Now, on top of that, just to be clear, you can run Linux on this aggregation, of course, right? You can also say, well, but I want this course to only be doing AI. No problem. You can still put RISC-V course here, run Linux here, and use this as your AI unit, right? So our point is, why make your life complicated buying an NPU with a strange ISA, buying a GPU from a very famous vendor, the only one that's left, with another very strange ISA, and then having a very nice RISC-V core. No, just have RISC-V everywhere, and you mix and match any way you want, right? Just to, my sales guys wants to say these things, right? So if coming down, right, you could say anyone can do this, yes, but we have it now, right? We have our Atrevido RISC-V core ready to go. It's out of order, and it's out of order on purpose to make sure that data is correctly and bring on time to the vector and the tensor unit. We have an out of order vector unit, we're probably the only people that have that, RISC-V 1.0, and you can configure how many bits you want in the vector unit, from very small 128 all the way to 2,000 bits. Your choice. I hope there's a customer in the audience, right? And then the tensor unit, again, you can configure from very small, a quarter tera up, all the way to 8 tops. So now you play with these 3 variables, and don't leave the room saying, damn it, I needed 20. He didn't have a 20 on the slide. Just put 4 of these, and you get a 32. And we can lower the frequency, and you get a 20 that you want, right? So all of this is ready to go. And we think this is that's why we call it all-in-one AI IP, and that's why we think that's how you should build your next SoC. One benchmark, very famous YOLO, on one of these elements, just one of them, right? One vector unit and one tensor by itself at the gigahertz is doing 33 frames per second. So that's real time. So it's just one, right? And yeah, you're going to say YOLO is not very advanced and blah, blah, blah. But it's just one of those elements. So you can put as many as you want. From 1 to 128, no problem, right? So you decide how much performance you need out of our technology, right? And closing, we're an IP company, so I have to tell you how we work. We are willing to customize everything I explained. So even if we think this is great, we know you may need a change. You may need something special in your silicon. We're happy to do those changes for you, whatever they may be. We're happy to put that on an FPGA so you can run your software, test your changes, make sure you're happy. And when you're happy, we hope to sign a deal, get some money from you, and again, we give you a license so you can go tape out, and of course, we support you all the way to tape out and beyond, right? So it's not goodbye on licensing signature, we support you all the way to tape out. And with that, thank you very much. I'll leave the summary here. We want to build the AI future with you. We want to build it with RISC-V, and we think we have a solution far superior to a patchwork of solutions that you can find today in the market. We know we have very, very good competitors, but no one has everything together in one piece. So we hope you'll come to our booth. We're one aisle down, and come talk to us, and we'll be happy to discuss with you on your next AI project. Thank you very much.